Lesson 8.1 Vibrations Part 2 Media and energy transfer vibrations require a medium solid, liquid, or gas to travel. The efficiency of energy transfer depends on the material's composition. Rigid materials, like steel, have strong intermolecular forces that allow vibrations to travel faster and farther. In contrast, less rigid materials, such as a pillow, absorb and disperse energy, causing the vibration to lose strength quickly. Lesson 8.2 Types of Mechanical Waves Part 1 Transverse versus longitudinal mechanical waves are classified by the direction particles move relative to the energy flow. In transverse waves, particles vibrate perpendicular to the energy like a plucked guitar string or a water wave. In longitudinal waves, particles vibrate parallel to the energy flow, creating regions of high pressure called compressions and low pressure called rarefactions. Lesson 8.2 Types of Mechanical Waves Part 2 Sound and complex wave sound is a longitudinal wave that requires a medium to travel. It cannot exist in a vacuum. While sound travels as longitudinal waves in fluids, it can travel as both transverse and longitudinal in solids. Many natural waves are complex, combining both motions such as water waves where molecules move in an oval path, or seismic waves from an earthquake. Lesson 8.3 Wave Characteristics 1 Geometric features waves are measured by their physical shape. Amplitude is the maximum displacement from the equilibrium point measured in meters for transverse waves or pressure for longitudinal. Wavelength dollar. Lambda dollar is the distance between two identical points, such as crest to crest. Phase describes a specific point's position, and a phase shift occurs when one wave is displaced relative to another along the x-axis. Lesson 8.4 Determining Wave Speed Part 1 The universal wave equation. The speed of a wave can be calculated using the universal wave equation, V equals F times lambda. Because frequency and period are related, speed can also be expressed as V equals lambda divided by the period. This equation is universal because it applies to all waves, whether they are water ripples, sound waves, or light. If you know any two variables, such as speed, frequency, or wavelength, you can solve for the third.
Lesson 8.5 Properties of Sound Waves Part 2 Speed and Intensity. The speed of sound in air increases with temperature, V equals 331.4 plus 0.606 T. Sound is also characterized by intensity, loudness, measured on the decibel, dB, scale. This scale is logarithmic. For every 10 dB increase, the sound intensity increases by a factor of 10. Long-term exposure to sounds above 85 to 90 dB can lead to permanent hearing loss. 9.3 Beats. The power of resonance. Every object has a resonant frequency, the frequency at which it vibrates most easily. Resonance occurs when an external force or wave matches this natural frequency, causing a dramatic increase in amplitude as energy is added efficiently. A classic example is pushing a swing at just the right moment to make it go higher. While resonance is useful for musical instruments, it must be avoided in building construction to prevent structural damage from large vibrations.
Lesson 8.4 Determining Wave Speed Part 2 Factors influencing speed. The speed of a wave is determined by the medium, not the frequency. In gases, higher temperatures increase wave speed because faster molecules transfer energy more quickly. In solids, speed is higher in more rigid materials. For waves on a string, the speed depends on the tension, where tighter strings are faster, and the linear density, where thicker, heavier strings are slower. Lesson 8.2 Types of Mechanical Waves Part 1 Transverse versus longitudinal mechanical waves are classified by the direction particles move relative to the energy flow. In transverse waves, particles vibrate perpendicular to the energy like a plucked guitar string or a water wave. In longitudinal waves, particles vibrate parallel to the energy flow, creating regions of high pressure called compressions and low pressure called rarefactions.
9.5 The Doppler Effect. Summary 1 Frequency shifts in motion. The Doppler effect is the change in the observed frequency of a wave when the source and the observer are moving relative to each other. When a sound source, like a siren, approaches an observer, the sound waves are compressed, leading to a shorter wavelength and a higher perceived pitch. As the source moves away, the waves spread out, increase in wavelength, causing the observer to hear a lower frequency than what was originally emitted. Lesson 8.5, Properties of Sound Waves. Part 1, Frequency and Ultrasound. Human hearing generally ranges from 20 Hz to 20 kHz. Sounds below this are infrasonic, while those above are ultrasonic. Ultrasound has many practical applications, particularly in medicine, because it reflects off different tissues, creating echoes. It is used to image fetuses, detect tumors, and even break up kidney stones safely. Beats. Damping and energy loss. Damping is the gradual reduction in a wave's amplitude over time, caused by the absorption of energy by the medium or by destructive interference. For instance, a child on a swing will eventually stop moving because friction and air resistance remove energy from the system. On a graph, damping is visible as a waveform that slowly shrinks in height while maintaining its frequency, eventually returning to a state of equilibrium. 9.3 Beats. Summary 1. Creating acoustical beats. An acoustical beat is a periodic change in sound intensity, loudness, that occurs when two sound waves with nearly identical frequencies interfere. As these waves travel together, they continually drift in and out of phase. When they are in phase, constructive interference makes the sound louder. When they are out of phase, destructive interference makes it softer. This rhythmic wobble between soft and loud is what we hear as a beat. The Doppler effect. Conditions for the Doppler effect. For the Doppler effect to be noticeable, the source must be moving at a speed that is a significant fraction of the speed of sound, typically at least 10%. Additionally, there must be a component of the source's velocity moving toward or away from the detector. A source moving in a perfect circle around an observer would not produce a Doppler shift. This effect is commonly experienced with emergency vehicles and is also used by police radar to measure car speeds. Lesson 1.3, Acceleration. Velocity time graphs. A velocity time graph shows how velocity changes over time. The slope of this graph represents the object's acceleration. A horizontal line indicates zero acceleration, while a diagonal line indicates uniform acceleration. Chapter 1, Kinematics in a Straight Line. Calculating displacement. Displacement is the straight line change in position from a starting point to an end point. It is calculated as final position minus initial position. Vectors can be added visually by joining them tip to tail to find the total resultant displacement. Lesson 1.4, Comparing graphs of linear motion. Summary 1, Acceleration time graphs. An acceleration time graph plots acceleration on the vertical axis. The area under the line on this graph represents the object's change in velocity. For uniform acceleration, the graph is a horizontal straight line. Lesson 1.2, Speed and Velocity. Position time graphs. A position time graph describes motion visually. For an object moving at a constant velocity, the graph appears as a straight diagonal line. The slope of the line on a position time graph represents the object's velocity. Lesson 1.2, Speed and Velocity. Summary 1, Measuring motion. Average speed is a scalar value representing total distance divided by total time. Average velocity is a vector value representing total displacement divided by total time. Motion at a constant speed in a straight line is known as uniform velocity. Chapter 1, Kinematics in a Straight Line. Lesson 1.1, Distance, Position, and Displacement. Summary 1, Scalar versus vector quantities. Kinematics is the study of motion. A scalar quantity, like distance, describes only the magnitude or how much ground was covered. In contrast, a vector quantity, like position or displacement, includes both magnitude and a specific direction, such as north or left. Lesson 1.3, Acceleration. Summary 1, Defining acceleration. Acceleration is the rate at which an object's velocity changes over time. It is a vector quantity measured in meters per second squared. If an object speeds up, slows down, or changes direction, it is undergoing acceleration.
Lesson 3.1, Types of Force. Visualizing forces FBDIS to solve physics problems. We use a system diagram to show all objects involved and a free body diagram FBD to show only the forces acting on a single object. Common forces include gravity Fg, normal force Fn, friction Ff, tension Ft, and applied force Fa. Lesson 3.3, Newton's second law of motion. Summary 1. The F equals ma relationship. The second law describes how the velocity of an object changes when a net force is applied. It states that acceleration is directly proportional to the net force and inversely proportional to the mass. This is expressed by the fundamental equation, F net equals ma. Lesson 3.4, Newton's third law of motion. Propulsion and interaction. This law explains how motion is generated when you walk. You push backward on the floor action, and the floor pushes you forward reaction. Similarly, a rocket accelerates upward because it pushes exhaust gases downward. The gases, in turn, exert an equal upward reaction force on the rocket. Lesson 3.1, Types of Force. Summary 1. Defining force and dynamics. Dynamics is the study of why objects move. A force is a push or a pull that can change an object's motion. Because it has both magnitude and direction, it is a vector quantity. The SI unit for force is the Newtonin, where 1 N equals 1 kilogram meter per second squared. Lesson 3.5, Using Newton's law. Summary 1. Complex problem-solving real-world scenarios often require using all three of Newton's laws together. This includes analyzing systems of multiple objects connected by strings or ropes, where tension Ft acts as a pulling force that is consistent throughout the connector. Lesson 3.4, Newton's third law of motion. Summary 1. Action and reaction. Newton's third law states that for every action force, there is a simultaneous reaction force that is equal in magnitude but opposite in direction. These forces always act on different objects, which is why they do not cancel each other out. Lesson 3.2, Newton's first law of motion. Summary 1. The law of inertia. Newton's first law states that an object will maintain its state of rest or constant velocity unless acted upon by an external net force. This tendency to resist changes in motion is called inertia, and it is directly related to an object's mass. The more mass an object has, the more inertia it possesses. Lesson 10.5, Seismic waves. Body versus surface waves. Body waves travel through the Earth's interior and include longitudinal P waves, the fastest, and transverse S waves, which only travel through solids. Surface waves move more slowly but are more destructive due to their lower frequency and larger amplitudes. By studying how these waves refract and reflect, scientists can map the Earth's interior and locate the epicenters of quakes. Lesson 10.4, Structural safety. Elastic flutter. The collapse of the Tacoma Narrows Bridge in 1940 was caused by aeroelastic flutter, where energy added by the wind exceeds the energy lost through damping. Unlike simple resonance, flutter involves the interaction between aerodynamic forces and a structure's natural vibrations. Modern engineers use mass dampers and structural stiffness to prevent these catastrophic amplitude builds in buildings and bridges. Lesson 10.5, Seismic wave. Summary 1. Earthquakes and tsunamis. Earthquakes occur when tectonic plates catch on each other along fault lines, building pressure until they suddenly slip and release energy. This release creates seismic waves that travel through the Earth. If the disturbance happens underwater, it can generate a tsunami, which is a series of massive sea waves that carry immense energy over long distances. Lesson 10.4, Structural safety. Summary 1. Mechanical resonance. A mechanical resonance is the transfer of energy between objects with the same natural frequency, leading to large amplitude vibrations. A classic example is sympathetic vibration, where one vibrating object causes another nearby object with the same resonant frequency to start vibrating as well. This energy transfer can be dangerous if it builds up in large structures. Lesson 10.6. Vibrations in aircraft. Aeroelastic flutter and the pogo effect. Aircraft must be designed to avoid aeroelastic flutter, which can occur if airflow over the wings causes uncontrolled, large-scale vibrations. Another unique phenomenon is the pogo effect in rockets, which involves unstable longitudinal vibrations caused by the interaction between the structure and the engine's thrust. Engineers use mass distribution and structural stiffness to ensure these vibrations remain within safe limits. Lesson 3.4. Newton's third law of motion. Summary 1. Action and reaction pairs. Asterisk. Newton's third law states that for every action force, there is a simultaneous reaction force of equal magnitude but opposite direction. These forces always occur in pairs and act on two different objects. For example, when you push a door open, the door pushes back on your hand with the exact same amount of force.
Lesson 3.5. Using Newton's laws. Summary 2. Connecting forces to kinematics. By combining Newton's laws with kinematics equations, we can predict the entire path of an object's motion. Once the net force is determined using a free body diagram, the acceleration can be found using the second law. This acceleration can then be used to calculate variables like final velocity, displacement, or the time required to complete a task.
Lesson 3.4. Newton's third law of motion. Summary 2. Motion through reaction. Asterisk. This law explains how motion is generated. When a rocket launches, it pushes exhaust gases downward. In response, the gases push the rocket upward with a reaction force. Similarly, when you walk, you push backward on the floor, and the floor pushes you forward. Even though the forces are equal and opposite, they do not cancel out because they act on different objects. Lesson 3.2. Newton's first law of motion. Summary 2. Balanced forces and equilibrium. Asterisk. When the net force acting on an object is zero, the forces are said to be balanced. In this state, the object's acceleration is zero, which means it is either completely still or moving in a perfectly straight line at a steady speed. Modern safety features like seatbelts and headrests are designed specifically to protect passengers from their own inertia during sudden changes in a vehicle's motion. Lesson 3.1. Types of force. Summary 2. Visualizing forces. Asterisk. To analyze a situation, physicists use two types of diagrams. A system diagram is a simple sketch showing all the objects involved. A free body diagram, or FBD, is more specific. It uses a single dot to represent an object and shows all the individual force vectors acting on it. Common forces include gravity pulling downward, the normal force pushing perpendicular to a surface, and friction resisting motion. Lesson 3.3. Newton's second law of motion. Summary 1. The F equals mv relationship. Asterisk. Newton's second law describes what happens when the net force on an object is not zero. It states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. This is expressed by the famous equation, net force equals mass times acceleration. Lesson 3.2. Newton's first law of motion. Summary 1. The concept of inertia. Asterisk. Newton's first law states that an object at rest will remain at rest, and an object in motion will continue moving at a constant velocity unless acted upon by an external net force. This property of an object to resist changes in its state of motion is called inertia. The amount of inertia an object possesses is directly related to its mass. More massive objects have greater inertia. Lesson 3.5. Using Newton's law. Summary 1. Solving complex problems. Asterisk. In real-world scenarios, all three of Newton's laws are often applied simultaneously to solve complex problems. This includes calculating the tension in the cables of a suspension bridge or determining if a locomotive has enough force to pull a heavy train through a mountain pass. Tension is a specific type of pulling force exerted by strings, ropes, or cables. Lesson 3.3. Newton's second law of motion. Summary 2. Factors affecting acceleration. Asterisk. This law explains why a powerful engine can accelerate a light car very quickly. while a massive truck requires much more force to achieve the same change in speed. If you double the net force acting on a constant mass, the acceleration will also double. However, if you double the mass while keeping the force the same, the acceleration will be cut in half.